morning, everyone, and welcome to another SIMM free webinar. This is the first webinar that we have two speakers, so it's quite exciting. I hope that everybody is ready to listen, to hear, and to learn. We have a very big privilege today to have two speakers with us who, without giving away, because they both look so young, their ages, have probably combined over 50 years of pyrometallurgy, industrial and academic research behind them. So I don't think that is something that one can often say when introducing two speakers. We've got Joalet Steenkamp and Eli Ringdalen, who's going to present to us today on the PreMa project, which is funded from European Union funding and has incredibly strong ties via Mintec and the South African manganese industry, and therefore has a very interesting background in terms of what is happening in South Africa to revitalize the manganese industry as well. So while I'm talking, Joalet and Eli can start loading the presentation. Because it is such a unique combination of very esteemed colleagues, the two of them will also introduce themselves as they start speaking. So for those of you who don't know them. So with no further ado, let me give way to the presenters and let's sit back and hear this interesting story about the PreMa project and how this has relevance in South Africa. Thank you, Joalet. Eli, very welcome today.
Thank you for the kind introduction, Isabel, and welcome everybody. It's nice to see there's so many people that dialed in and listening today. So my name is Joalet Steenkamp. I work as a chief engineer at Mintec in the pyrometallurgy division. And as Isabel said, I have quite extensive experience in pyrometallurgy, both in industry and in research. I'm passionate about pyro. So what we're going to talk about today is the PreMa project, and I will contextualize it for you in the context of the manganese ferroalloy industry in South Africa. So the outline of the presentation, first there will be some introduction. I will tell you about South African production. I will also introduce you to the concept of the schools on manganese ferroalloy production. Eli will discuss the PreMa project with you, outline of it, and then I will tell you about the Mintec pilot project that's form part of the PreMa project. So manganese ferroalloys, there are basically three grades produced, all in South Africa. You get high carbon ferromanganese and silica manganese, and they are primary alloys, and they are produced from ores then basically. And what you'll notice here is that the high carbon ferromanganese has a high carbon content, 7.5%. Silica manganese has much lower carbon content, but a much higher silicon content, 12.5 to 21%. And then medium carbon ferromanganese is produced from high carbon ferromanganese, and the carbon content of the alloy is reduced. What you see at the bottom is silica manganese alloy on the left being layer cast, and then you see the silica manganese heap in front of the metal treatment plant, and on the right hand side you see a piece of silica manganese in one of my younger colleagues' hands. So the main use of manganese ferroalloys is in steel making. It's an alloy added to steel. It was actually had a breakthrough for the PreMa process that produced steel making, or was developed by PreMa. We could add manganese to the steel to deoxidize it. And what they also found is that manganese not only reacted with oxygen, but also with sulfur. And in that sense, could increase the toughness by decreasing the shortness of the steel. So manganese is an important alloy. It's very low concentrations, mainly in steels, less than 1%. And what you see on the right-hand side here is a map of steel production in 2018. And the bubbles that you see is not the spread of coronavirus, which we have all seen recently a lot of, but actually the size of the producers. And China is dominating, but there's also significant production of steel still in the USA and in India and even in Europe, which I found very interesting. And then here at the bottom, in South Africa, we also produce steel. Manganese itself, manganese alloys, is also 90% is used in steel making, but it's also used in aluminum production, copper, manganese, and zinc alloys as an alloying element. But there it would mainly be the electrolytic manganese that's used. Manganese is also used in batteries and chemicals as different compounds. On this map, you see where manganese ferroalloys are produced, and you will notice that it is a truly global commodity. It's produced worldwide, and in South Africa, we also have a significant production of manganese. We'll look at the distribution in the next slide. The main producers are China and India, and you'll also notice that we have producers in Norway, in France and Spain and Slovakia. So that's our European partners, and that is important in terms of the PreMa project. We have been collaborating with the Norwegians for a number of years. Personally, I've been collaborating with them since 2010, and we've walked a long road together, which has been very fruitful. On this slide, on the left-hand side, you see silica manganese production. It's actually much more than high carbon ferromanganese. Steel producers prefer the silica manganese because of the type of inclusion that's forming the steel. If they don't use silica manganese, they use ferrosilicon and high carbon or medium carbon ferromanganese production. And my understanding is that the inclusions are different, which creates problems downstream with the casting and with the processing of the steel. You'll notice that for silica manganese, China is the main producer, and I'm really happy to see there's people from China even listening today, so welcome. And then also high carbon ferromanganese, China is a significant producer. India, you see featuring there. And then on our side, South Africa has produced 1% of the silica manganese and 4% of the high carbon ferromanganese produced in the world. Norway, you'll see features 2% of the silica manganese and 2% of the high carbon ferromanganese. So in terms of processing routes, I'll start with the processing routes followed in South Africa. And the routes, the choice of route are driven mainly by the choice of ore available. So in South Africa, we produce both high carbon ferromanganese and silica manganese from ore. So ore is the main source of manganese. We use carbonaceous reductants, coke, anthracite, and bituminous coal, and then fluxes. The main flux in South Africa that's used is quartz. In both instances, CO-rich off-gas is produced by the process. When you have an open furnace, the CO gas gets combusted on the top of the burden. So the off-gas that's produced and cleaned afterwards is CO2 rich. In a closed furnace, the CO gas is captured and cleaned through a wet scrubbing system. The combusted gas is cleaned through a dry baghouse system. And then in both instances in South Africa, the slag gets discarded onto slag dumps. So here you see the composition of the slag, and what it's mainly driven by is that our ores are rich in carbonates, and that's why we have such a high CaO content. Calcium carbonate and also dolomite. And I see my colleague Triti is also part of the audience today, and she's a total expert on this. So if anybody wants to know more about manganese, there's just a way to go. But you'll notice the basicity of the discard slag. Practice is 0.9 and 0.5. Remember those numbers when we go to the next slide. What's done in Europe is and elsewhere is they follow what they call a duplex route, where they feed ore for the production of high carbon ferromanganese, produce a slag rich in MnO. Slag composition at the bottom, the MnO of the slag is 40%. They can do that because they have a lower basicity ores. They import their ores not only from South Africa, but also from Gabon and from Australia and elsewhere. And Eli can tell you more about that. So what they do is then feed that slag into their smelters to produce silica manganese. In this instance, the slag produced in silica manganese production is also discarded. Also, these furnaces tend to be closed, so they collect the CO-rich off gas. And there's a lot of interesting things that people do, like heating water, heating even in Norway they heat some of the sports fields so that they can play sports in winter using the CO-rich off gas, combusting the CO-rich off gas. So in all these instances, wet scrubbers are used. So for those of you that's not familiar with ferroalloy production using submerged arc furnaces, this is a slide that was taken from a presentation by Professor Marette Tangstad. And what you see on the left-hand side is a submerged arc furnace. The electrical energy is supplied via three what they call Söderberg electrodes. So these electrodes are very, very wide in diameter. 1.6 meters is not funny a number, it's a typical number. And the electrodes need to be baked while production of the alloy is taking place. So it's quite a complex process to manage your electrodes as well as your process itself. In manganese ores, the carbon materials or fluxes are fed through feedballs in the roof. And then what you see is a burden of material forming on top of what we call a coke bed, which contain coke and slag, and then the alloy layer. So this burden of raw material, as it moves down towards the bottom of the furnace, a gas reaction takes place. So your higher oxides of manganese and iron gets reduced. And by the time it reaches the wet coke bed, which consists, as I said, of slag, liquid slag, and carbonaceous reductant, you have your iron, that's if you have a properly operated furnace, that's already Fe, metallic iron, and you have your MnO that dissolves in the slag and then forms where the final reduction takes place of MnO to Mn. Your quartz is also dissolves also into the slag, and from there it's reduced to silicon. And you have carbon that dissolves into the alloy. So high carbon ferromanganese production is both high carbon and silica manganese is quite electrical energy intensive, with numbers between 2.2 and 3.2 megawatt hour per ton for high carbon ferromanganese alloy production, and for silica manganese 3.3. So why do we produce manganese ferroalloys in South Africa? There's a number of reasons, and one of them is that we have the Kalahari manganese field in the Northern Cape. And this is also from Desh's publications. You'll see it's a town near, or the borders at a town called Hot as Hell. It's not spelled like that, but that's how you pronounce it. And it's really, really hot there in the Northern Cape. It's a semi-desert. It was discovered there in 1907. And in 2020, the numbers that I got recently from the USGS, we have 74% of the world's identified manganese resource and 32% of the reserve. In other words, 32% of the ore that can currently be processed to produce manganese ferroalloys worldwide. So the South African ferroalloy industry, the pioneer that basically started it was Hendrik Johannes van der Bijl. And we have Van der Bijl Park named after him. There's a number of places where his name featured. And what's interesting, I read a bit of his biography, and it's really interesting to read, the interesting read. He was the fellow of the Royal Society, which thanks to our corona fight and the person that leads that for us, we now know that it's actually very prestigious accolade to have. He was born in 1887 in Pretoria, and he did his undergraduate qualifications here, obtained at the University of Stellenbosch. And then in 1912, he got a PhD in physics from Leipzig University in Germany. He went after completing his PhD, he went and worked in the USA. But in 1920, President Jan Spitz brought him back as a scientific and industrial advisor in the departments of mines and industry. There he established, his first task was to establish Eskom, which is our power supply company in South Africa in 1922. In 1925, he established ISCOR, which is was the steel producing side of the chain. Today, ArcelorMittal is still the steel producing side, but ISCOR was unbundled from the unbundling of ISCOR. A number of companies was established a few years ago. And then in 1937, Armcor was established for the production of manganese ferroalloys, and today it's called metalloys. That is not the only achievements that this really interesting person did, but for our discussion, I think this is major achievements for him, and he died in 1984. So, as I said, Armcor was established in Newcastle in 1936. They started to produce high carbon ferromanganese using a blast furnace. And then in 1942, a 3 MVA rectangular electric arc furnace was built. That's the same size as the largest furnace at Mintek, and that was used for the production of the alloy, so it was a production furnace. In 1951, they relocated to Meyerton, and today itself, 32 is metalloys plant. Assmang was established in 1957 in Cato Ridge near Durban, and in 2011 they converted the Machadodorp plant also to high carbon ferromanganese production, but that plant has been mothballed. TransAlloys was established in 1960 as a ferrochrome plant. In 1976 it was converted to a ferromanganese plant, and today it's still our only silica manganese producer. And then Palmit Chrome Corporation was established in 1963 to produce ferrochrome. In 1990s, it started to produce silica manganese. It's known today as Mogale Alloys, but also their furnaces are more. So currently we have the 3 producers: Metalloys, Assmang, Cato Ridge, and TransAlloys. And what you see here on the map is the location of the ore body and then the location of the smelters. Over the past 15 years, the average electricity tariff in South Africa increased by 250% in real terms. And that resulted in plant closures, with a significant reduction in installed capacity, plants being mothballed. So the only ones in operation, Metalloys, Assmang, Cato Ridge, and TransAlloys produce Metalloys and Assmang produce high carbon ferromanganese. They don't necessarily run at full capacity at this stage, but 50% or less, and they also produce medium carbon ferromanganese using converter technology. TransAlloys, as I mentioned, produce silica manganese, and they run at full capacity. So in 2012, I established through the SIMM, the School of Manganese Ferroalloy Production. The main presenter there was Professor Marita Tangstad, who is the world expert on the production of manganese ferroalloys. And myself and Eli Ringdalen, we also participated in that. Then in 2016, we hosted SIMM hosted the second school on manganese ferroalloy production. Again, Marita Tangstad was the main producer, and Eli and myself participated, but we also brought in more researchers from South Africa. Part of that school was a workshop, and I would encourage you to go and have a look at the results of this, which was published in the Journal of the SIMM. But there was and the purpose of this workshop was to create a research agenda to increase the production of manganese ferroalloys in South Africa. We do export a significant amount of ore, and we only beneficiate very little of the ore locally. So we're looking into ways in which we can support the local industry and maybe also grow it. And there was 95 ideas produced, 50% to support existing producers and 50% of the ideas to to maybe develop new markets or find new ways of producing these alloys. And one of the support ideas was then to look into preheating or pre-reduction of the ore. And that, I will give you that, because that's where the PreMa project comes from. And at that meeting, Dr. Ringdalen committed herself to find funding for us to continue collaborating on maybe doing more work on these ideas. And she actually delivered on that. So the third school on manganese ferroalloy production was scheduled to be hosted in South Africa in June this year, in Katu, which is close to the ore body. But thanks to the coronavirus, we decided to postpone it. At this stage, it's tentatively scheduled for October in Cape Town. But another option would be to host it as a webinar series. And your thoughts on this, I would really appreciate. So here I've already told you about the series of schools and the workshop we hosted, and what you see here is all the faces of people that participated in the workshop to generate ideas to take the industry forward. So now I will hand you over to Eli Ringdalen.
Thank you, Joalet, this presentation. And my name is Eli Ringdalen. I'm a senior research scientist at SINTEF in Trondheim. I've been worked for many years in the industry, in several different industries, and manganese production. And now I'm working with research and production in between all of those. So, and I'm very glad that Joalet showed us that this workshop, that it really ended up with a project. Because we really did some work, we planned the work, and we ended up with the PreMa project. And the aim of the PreMa project, that is to reduce the CO2 emissions and the consumption of the electrical energy in the manganese alloy production. And if you look at the slides here, to the one at the top, you see that is how we think it is now before the PreMa project. As it is now, you have the manganese ores, the electrical energy, and the coke that goes into the furnace. And the manganese ores have different oxygen contents. And then you end up with the manganese alloys, ferrosilicon and silicomanganese and ferromanganese, as Joalet explained. What we want to do with the PreMa project is that we want to install a pretreatment unit before the furnace. And this pretreatment unit will feed the manganese ores into it. I just had some problems here, technical problems. Yes, we'll feed the manganese ores into it as to the furnace, and then we will feed some additional sources of sustainable energy sources: CO-rich off-gas, biocarbon, and thermal solar. And by this, we will pre-treat the ores, so they will become heated. The water will evaporate, and we will also have some pre-reduction of the higher manganese oxides down to lower manganese oxides. So this means that from the pretreatment unit, we will feed the ores, the heated ore at 600 degrees into the furnace, and we will produce the manganese alloys as earlier, but we will still need electrical energy and coke, but you will need less of it. And some of you may ask, why do you need less coke from this when you still have done the pre-reduction, since you have produced it only down to MNO maximum? And that is because we will then have less of the boudoir reaction in the furnace. So we will use less unintended manganese or unintended carbon there. Next slide. The PreMa project, that is an Horizon 2020 project from EU. It started in 2018, will go to 2022. We have a budget of 12 million euros, the total, and 10 million euros is paid by EU. And I must add that in this EU project, also the industry producers get covered their costs, at least most of their costs. So some of this budget is also for the industry producers. The project that is, we have included all the manganese alloy producers in Europe, in Western Europe, and that is Ferroalloy in Norway, France, Spain, and it is Eramet that is in Norway and in France. It's Webset that is in Slovakia, and we are lucky to have with us also one South African manganese alloy producers, that is Transalloys. In addition, we have two of the equipment suppliers, that is both Autotech Germany and Autotech Finland, that were part of the development of the equipment. We have the research institutes within metallurgy. It is the SINTEF in Trondheim, where I come from, and it's Mintec, where Joalet comes from. In addition, we have the Deutsche DLR, the Deutsche Zentrum für Luft- und Raumfahrt, looking into the thermal solar, and we have HSZDR, looking into the that is investigated the flow sheeting, and EATU, that is working with the communication. In addition to those, we also have the universities, NTNU in Trondheim and Stellenbosch in South Africa. And I'm the coordinator of the project of the SINTEF, is the coordinator institute. And SINTEF is a research institute in Trondheim in Norway. We are an independent and non-profit research institute. And we earn all our income from contract research and development, so it's not by state funding. We have a turnover in 2018, so 330 million euros, 2,000 employees, and 70% of these are researchers, mostly with PhD. And we do research within a lot of different areas, and metal production and processing is one big one of those. Yes, next slide. So, PreMa project, why do we do this? What will we gain? The main gain of the PreMa project is to reduce the electrical power consumption, and that will be in the order of 25%, according to the plans. We also will reduce the CO2 emissions in different ways. And that to achieve that, when reducing the electrical power consumption, will reduce the electrical energy consumption when the electrical energy comes from coal-fired power station. In Norway, most of our energy comes from hydropower. That will be the case. And you must also use green sources of reductants or green methods for pre-reduction. In addition, we also will reduce the CO2 emission because we have less of the unwanted boudoir action inside the furnace. Other advantages is that we will remove water and CO2 during the drying and calcination step. That will give a reduced risk of explosions. But they also increase the possibility to use fines fractions in the feed, and especially in the closed furnaces that we have a lot of in that furnace type in Norway. It will also give a more stable furnace operation due to the improved management of carbon balance, with the benefits of that, as especially also related to that we have less of the boudoir reaction. Next slide. And this is not, we're going to have it up to industrial level because it's not a new technology. I think most of you at South Africa knows that you do some pre-treatment in the chromium ores, and it's also done industrially with the manganese ores, and it's done at the Kashima works in Japan. And there, if you look to the right at how they have the production, they have the electric furnace, and that the main idea from Kashima works that they wanted to reduce their consumption of electrical energy in the SAF furnace, so Magarch furnace, because I think availability of electricity. And then they introduced their pre-reduction unit before, and this is coal-fired, so it will not give any reduction in the CO2 emissions as we aim at in PreMa. And they use and also gas with off gas from the furnace with 500 degrees. They feed the raw materials with 600 degrees into a submerged furnace, and together with some melt, and then add some melt, and then they produce slag and metal. And if we look to the left at the curves, to see what is the effect of that on the consumption of electrical energy in the submerged arc furnace. And this is only for the submerged arc furnace, not for the total system. And if you look at the red bars, that is for the virgin ton and not including the remelt. And this has been recalculated to the blue one to be able to compare the theoretical calculation with the real achievement at Kashima Works. And what you can see from the non-pretreatment to the left, it's around nearly 2,700 kilowatt hours per ton they had there. And if they calculated what could we gain in different steps of pretreatment, heating, carbonate depositions, some of the reduction to the high that will reduce it, some can get some increased consumption because you lose some of the exothermic reactions in the furnace, and move them over to the pre-reduction instead. But at the end, you will have reduced the consumption of electrical energy with around 400 to 600 kilowatt hours per ton, depending on how much you pre-reduce it. And this is a considerable amount, and this has been done for several years at Kashima Works. So, next slide. Since we also are looking into the renewable sources, sustainable energy sources, we looked into what we have that is really available. And then if we look into a closed submerged arc furnace, and this is a ferromanganese, and it is from an example in Norway. You can see to the left that the total energy you put in, about a little less than half of it is electrical energy. And if you look at to the right, you see that most of the energy you put in ends up in the chemical energy in the metal, a little more than half, a little more than you put in of the electrical. But a lot of the energy ends up in a lot of different other streams. And the largest one of these is the chemical energy in the gas. It is not so much the heat of the gas, but the chemical energy in the gas, because you have a closed furnace with CO gas. So for pretreatment of course, we identify this as a natural stream to use that is not often energy that is not often used at the place and is available at the place. Okay, next slide. So then what do we really want to do? Again, this is given some of the background, but now what do we really want to achieve in the PreMa project? What is our aim? And the overall objective is that we are going to demonstrate a technology for pretreatment of manganese ores. That means that we will have it up to the level where it's close to industrialization. And the technology should be able to increase the energy flexibility, energy efficiency, and also enhance raw material use of fines and reduce CO2 emissions in the production of manganese alloys. We'll look into doing this by demonstrate various pretreatment technologies that are going to use different energy sources like CO-rich industrial off-gas, biocarbon, and solar thermal. So all of these will be developed and demonstrated. And we will bring it up to be ready for industrial implementation by design, engineering, making design, engineering, cost figure, and impact for the industrial full scale to make this together with a business plan for the industrial implementation. And the goal is to have this ready when we have finalized the project. Next slide. But this does not come by itself. It requires a lot of work, a lot of investigations, and we have planned to do a lot of investigations. First, the pretreatment, how it affects the pretreatment vary a lot between different ores. So we have chosen 3 different ores that we are going to investigate, and also 1 actual charge mixture, because most of you use mix different ores in the charge mixture. And we are going to study to get a lot of knowledge about these and the properties and how they are affected by pre-reduction. We are going to look into different energy sources: thermal solar, CO-rich off-gas, biocarbon, and also a mixture of the CO-rich off-gas and the solid carbon. And then, of course, we need the technologies, and we have planned to investigate the 3 different technologies: rotary kiln, fluid bed, and the shaft furnace. And the next slide. Just mention for the thermal solar, that is maybe very relevant for South Africa. I assume most of you know a lot about it from what Lina has been working with. But the main idea here is to concentrate the energy of the heat from the sun, so you can warm up air up to 800 degrees and then preheat the ore with this air. I think this is it can be very relevant for South Africa, Southern Europe, but maybe not so much used in Norway. Next slide. And to come up to the level we want to be, we need to do some close to industrial scale. It is not enough with the laboratory experiments. We will need to do some pilots. And we have planned several types of pilot. First, to the left there, you see the tree one there. We're going to investigate the pre-treatment and pre-reduction technologies in different pilots. And this will be done in batch scale and producing around 1 ton, half a ton, or 1 ton of material minimum. And first, the rotary kiln will be investigated by Eramet IDs, or what is early Eramet research. And in fact, they have already run experiment in the rotary kiln. Autotech will also investigate the rotary kiln and also plan to investigate the fluid bed at their laboratories to run experiments there. In addition, we want to look into the possibility to use a shaft furnace, because that was planned at Fellow Globe, and here this will not be that will be connected to the industrial production by using industrial off gas. So we'll take industrial off gas from a closed furnace and with the composition of that, and use that to pre-treat the material in a pilot shaft furnace. From all of this, we will produce the material that is produced in this pilot will not be taken back to industrial furnaces. It will be cooled down, and then but we need to know how will the pretreatment affect the furnace operation and how much we gain from CO2 emissions. So material from all these pilots, around half a ton or 1 ton, will be brought to SINTEF and NTNU, where we'll run 11 pilot tests to submerge with the pilot submerged arc, where we can feed around 0.5 to 1 ton of material. And then we will first run the experiments that when the material is not pre-treated, and afterwards with the same type of ore material that is pre-treated. And that will be, and then we will compare this, and also based on that calculate the effect. But the main and important thing that we will not be able to investigate by this method, that is a really important challenge. That is the feeding of warm material from the pretreatment unit to the submerged arc furnace, and that is critical to get the energy and CO2 advantages we want. And this will be done in a large-scale pilot at Mintec, where they will run for several weeks, where they will have combined both the pretreatment unit and the feeding and the submerged arc furnace. And the results from this will be combined with all the other pilot experiments to give us information about the effect of preheating on pretreatment with the different technologies. But I think this is very crucial that we are able to have this long-scale pilot, and to also to do the feeding of the raw material. And Joalet will tell you more about that. So, Joalet.
I'll repeat that. What we call this facility is the Bay 2 preheat facility, because it will be installed in Bay 2 of Mintec. Mintec has 7 bays where we host our pilot facilities. It's a joint facility that's being developed between the PreMa project and the TIMAC project, where the PreMa project looked at integration of a preheating system, and we decided for financial reasons and other practical reasons to buy a rotary kiln, electrically heated rotary kiln, to heat material. So for the PreMa project, that kiln will be integrated with the AC furnace, which will be operated in submerged arc furnace mode. The TIMAC project will look at the reduction of titaniferous magnetite in a DC open bath arc furnace. So for the TIMAC project, the kiln will be coupled with the AC furnace, not with the DC furnace. What we do share is an integrated materials handling system, product handling, and water cooling system, and I'll show you a bit more of the details about it. So the purpose, as Eli said, of the PreMa project is to study the coupling between the preheater and the AC side. We know from industrial scale ferrochrome smelters in South Africa that has preheaters integrated in their flow sheet, as well as ilmenite smelters that has the different types, but also preheater integrated with the flow sheets. That unstable operation of the preheaters destabilizes the submerged arc furnace or the DC smelter in the case of ilmenite smelting to such an extent that the plant operating personnel decide to rather switch off the preheater. So they rather take the penalty on not drying or preheating the raw material and have a stable furnace operation than combining the two. So what we want to do is understand that coupling much better, both for the PreMa project and the TIMAC project. So what we'll do with the campaign, it's a 3-week campaign for PreMa. We will study the effect of cold feed versus hot feed on smelter operations, and we will focus on electrical energy consumption in the smelter as well as CO2 production, because those are the two primary criteria of the PreMa project. For the TIMAC project, the project is managed by my colleague Eli Ringdalen, that many of you are familiar with. As I said, it will study the coupling between the preheater and the DC arc furnace, and specifically for titaniferous magnetite smelting. And again, he will also he plans more than one campaign to study the effect of cold versus hot feed on the DC furnace operation. So the design, we had to evaluate for cold feed versus hot feed up to 900 degrees C. For PreMa, we're going a bit lower. And how we're doing the project, we've done the basic engineering, and I will show you the results of the basic engineering. We are busy currently with the detailed engineering, or at least getting the orders placed for the detailed engineering to happen. Again, the whole lockdown experience has stuffed around our schedules, but we will manage that. So in terms of the basic engineering, first step was to design the block flow diagram to identify the function in each step of the flow sheet and then describe that in the functional specification. And then the second step is to add specific equipment and the flow of materials, where we produce the process flow diagrams and we describe the process specification. So this work was summarized and published and presented at TMS this year in February, and I hope I provided a link for that paper if you want to have more details on it. But what I show you on the left-hand side is the block flow diagram, and on the right-hand side what we have in place, or then what we intend to design. In terms of raw material handling, we can receive material in bulk, what you see in the top left photograph, material in bulk that we store covered with tarpaulins, and then we can take it, the next step would be to dry it in a shed, and then we can bag it in bulk bags. We use bulk bags as part of our feeding management of our feed system. Or if we can also receive material that's already in bulk bags. And this is a standard, this facility is already there, and it's used frequently when we run campaigns. For the DC furnace, we will want to feed either cold material directly into the furnace or the material via the preheater to the furnace itself. And there on the right-hand side of this sketch, you see the feed system. We have 4 bunkers that can feed the rotary kiln to the back. You see the bucket elevator there feeding into the rotary kiln to preheat materials, or the materials can be, there's also 4 bunkers that can feed into the bucket elevators, feeding then cold feed into the furnace. we will be able to run that simultaneously. And what you also notice on this slide is the DC furnace has one electrode. Then on the AC furnace, it's the same feed system with a slight modification. And what we have here is a mixing bin on the outlet side of the rotary kiln, and we will feed our raw materials. So we'll feed our ore through the rotary kiln, preheat the ores, and then we will feed the flux and the reductant into the mixing bin, and from there feed into the furnace. And you'll notice we'll have the 3 electrodes there. For furnace tapping, we can either have bi-level or single-level tapples. For the DC furnaces, we typically have bi-level tapples, so the slag tappel is slightly higher than the alloy tappel. We tap alloy into ladles, and what you see on this one here is the slag being tapped in a slag pot. You notice our fume extraction system, and this is one of our existing furnaces that we have. But we will duplicate this system also in bay 2. And then for the AC furnace, we have a single level tappel, and what we'll basically tap into our ladles, both alloy and slag, and then once everything is cooled, solidified and cooled, we'll separate manually. So then we take our, once cooled, we go and tip the ladles or the slag pots then in the product handling area, where we then, if needed, separate the alloy from the slag. You see here on the left hand side to the back there's the slag dump, and on the right hand side at the bottom there you see our ingots. That's the alloy ingots that gets well, we store that in a special facility that's more controlled, and that is also typical for our operations, and we will do the same here. In terms of off-gas handling, Bay 2 has a baghouse system. So what we do on both furnaces, what we'll have is a slip gap between the furnace roof and the offtake for the off-gas. We will combust the off-gas. So all CO that form will be combusted there, and then the gas gets vented basically through this duct. Cool down, the dust gets removed in the baghouse, and the clean gas gets into the atmosphere. And then we also have a water cooling plant. The water cooling plant you see on the right hand side, I marked there in a white block. That plant supplies cooling water to all 7 of the bays, and it will also, we have dedicated pumps supplying water to our system wherever we need it. Here are some of the design parameters, and yeah, there's the link to the paper. So if you want to see, there's another paper that I presented at TMS, which has the fact sage calculations that I use to do a mass and energy balance. Basically, to specify the power supply, which we will buy, and also the feed system, the feed requirements. And already the next steps, as I said, we'll do the detail engineering. We need to finalize the process description and the PFDs. We need to develop the process control strategy and the piping and instrumentation diagram. We have a colleague, Ashley Davey, that's excellent with that. He's already working on it. So we will do this, the control we will do in-house. And then we'll do the final selection of equipment, components and instrumentation, specifically for the feed system and then 2 furnaces, and do the detailed engineering of mechanical and civil structures. What you see on the photograph here, as I said, we bought a kiln to preheat the material, and it was delivered on site earlier this year, February. So thank you for your time and for listening, and I look forward to all the questions. That's it from our side, Isabel. Thank you.
Thank you, Joalet and Eli. I think that was very comprehensive. A lot of people don't always know what we do and how these projects work and fit together, especially people who don't particularly work directly in the research industry. So it's always great for us to share how these projects are put together. And it's not just easy. You guys didn't just walk up to the EU and say, please give us money. It took a lot of hard work. And I want to congratulate you guys on all of that. And then also this whole, I think the message for today is just how amazing it is that we can collaborate, Norway and South Africa being so far apart. So I'm very excited about that as well. So there's a few questions. I'm just going to go back on the chat because some people are, so there's Harman Autogum asking, do you expect challenges with the hotter feed as it may reduce the condensation of volatilized manganese, or any advantages as for potassium and phosphorus can be eliminated better and being prevented from recirculating? If anybody, I don't know, either one of you can answer.
Should I answer that, Joalet, or do you want to answer? Yeah, I think that with I do not see from this. We do not see that it's so much of a recirculation of the manganese in the furnace, because since you have in the coke bed and the ferromanganese and silicomanganese, you have around 1500, 1600 degrees, and it's so it's. I do not think that will affect it much, and I do not think we'll have any recirculation of manganese in the pretreatment either. But we will have an advantage from the pretreatment unit, because then we can have some of the alkalis that you normally can recirculate in the furnace. We can maybe drive off some of them, and the recirculation of alkalis in the furnace, or the level of alkalis in the furnace, will affect the boudoir reaction and the consumption of carbon materials. But it might be an advantage, but maybe it will just build up the equilibrium level in the furnace in a way. We do not know. But I don't think that even if we preheat the material, we will also still have the ores into the material, the same charge mixture. So if you think that will condense in the furnace, that could do it anyway. But I will also add that I have been through a lot of excavation of manganese furnaces, several excavation of industrial furnaces, and it's not much condensed material to find in those. Okay.
Joalet, do you want to add anything, or are you happy for us to
No,
skip?
no, I'm happy.
Okay, so this is a question, I think, that in the scope, but it is obviously a valid question, is will anybody be looking to recover waste heat from the tap slag, such as, for example, dry granulation?
I think it's a valid question, and I think also something that one need to look into. But at this stage, we also need to work within a specific budget, so we are limited in that sense. But there's no reason why, it's not it is definitely something that we can look into, and that Mantic has been discussing in-house. Yeah.
Yeah, I think the question is that it's not in the scope of this current project, but it is obviously a valid technical question. I mean, when you talk about energy optimization, recovery of energy is one of the topics that it is, but it's not, this case, it's not a recovery of energy project, but it's obviously, and there is also, Infocon in 2013 had a section on energy recovery. So there's a lot of nice papers published if you go to the Mantic site under Infocon. Quite a lot of papers have looked at that. So there is potential, I think. Another question that's come up, and I think that is if you listen to the presentation presented by Lena the other day, has Mantic ever investigated the techno-economics of establishing a ferromanganese smelter at the ore source, where there's lots of space?
Yeah, Mantic, we didn't do it ourselves, but we are aware of projects that people are doing or have done the techno-economics to look into doing exactly that, because one of the three cost drivers for the smelters is the transportation of the ore, the cost associated with the transportation of the ore. And I think when you have it close to the ore body, you cut away, basically reduce that. I think in the past, why it did not happen was the unstable power supply. The reason why we have the smelters on the Highveld is because we have all our power plants here. But now that we have such big solar resources opening up there, power supply, power plants opening up in the Northern Cape, I think that argument is not valid anymore. The other thing is, of course, you need to have a market for the product to make your project financially viable, and I think that is where the challenge comes in. There's oversupply internationally of the alloy. So it's not something that we have done actively, the work, but it has been done. It is being done in South Africa, and I think it's something that we can continue to look into because it makes sense.
Yeah, I think that there is actually quite a lot of work happening, perhaps not directly under the PreMa project again, but in the sort of renewable energy or the integration of solar thermal energy. And I mean, anybody who's interested in that, keep an eye on social media as we load the webinars from the past 2 weeks on the SIMM sites. You can go and re-listen to the work that Lena presented on. And she's done a lot of partial work on terms of feasibility studies and techno-economics as well on some of those aspects. So,
I just wanted to add to that, but because I think that since we in the PreMa project is doing a lot of work with the thermal solar to demonstrate it and to develop further, that will also be a benefit for other that is going to use it in other types of technology, other places, and so on. So even if we are not looking into this specifically, it will give some knowledge and competence that can be used.
Definitely, it's definitely applicable across a lot of the disciplines. We have a question here from Quinn, who says, are the smelters used in the duplex process in Europe more or less the same as those used in the separate silica manganese high carbon ferromanganese process in South Africa? Or are there significant differences in terms of the pre-treatment, design, operating philosophy? Let's answer that one first.
Yeah, I think it's in principle the same furnaces. The furnaces in Norway are closed furnaces, and the furnaces I think most of them you have in South Africa is open furnaces, and that's a big difference. But that is the difference of how you take care of the off gases and so on. I think it's and another difference is that in the closed furnaces you cannot use so much fines, but the design of the furnaces is in principle the same, and I think it's also possible to. I've seen that they can build open furnaces to closed furnaces.
Yeah, I think the trend generally is, I mean, if you look at ferrochrome, is towards closed because of all the other benefits, but it is an interesting perspective to ask the question, closed versus open. Thanks, Eli, for that. I think that was very nicely answered.
I think also that, I want to add to that, the big difference is in Europe, when they use the duplex process, is that they produce a slag in the high carbon ferromanganese smelter with a significantly higher MnO content than what they produce locally. So it's 40% versus 20%. I mean, that slag you can take through silica manganese. And also what will happen is you will reduce your phosphorus in your high carbon ferromanganese production, which will then result in, potentially can result in a lower, in silica manganese with a lower phosphorus content. So I think that is the two, to me, from a process flow perspective, the two things that are significant.
I think the main difference is that it's the operating philosophy that you use and the ores you use, because in the duplex process, if you have very much you need to produce you can either produce a slag that you can be a discard slag from the ferromanganese, and then you have another basicity, as you told earlier, compared to when you are going to use a slag with a high manganese content. So then you can operate your ferromanganese furnace in a different way and with a different type of raw materials.
Yeah. I think you answered also sort of partly the question that he asked secondly, do you expect the impact and effectiveness of the PreMa technologies to be different in different parts of the world? And I think that you sort of already alluded to that, but if you want to elaborate on that.
I can say that I think that if you use, it depends on if you have a closed or an open furnace very much. I think that is a big impact, and then you can, that will affect if you have the CO gas for the pretreatment, the energy on the place. Another thing is that if you are using the duplex process and you are using a high amount of ferromanganese slag, it is easier to pretreat it because you will not have the higher manganese oxides, so you will not pretreat it down. So you start with MNO anyway, and then you will, in the furnace, when you have that, you will not have the problem that you will have unintended consumption of carbon due to the boudoir reaction. So you will not have that benefit, but you will have the benefit that it is easier to pretreat the material. So I think it's some pros and cons of both of them.
Yeah, and I would like to add is that I think if you implement the process anywhere in the world where you produce power, your electrical energy, electricity using a coal-fired power station, the influence or the benefit of the project will be much more significant. A 10% reduction in electrical energy requirement of the furnace will be much more significant in terms of the CO2 emissions than when you have hydropower or so.
Yes, absolutely. So in South Africa, you will to use this technology in South Africa will contribute much more to reduce CO2 emission than in really Norway.
Yeah, so it's all relative. It's actually the answer. So this is a question that so I will preamble the answer because I'm very passionate about it. But Harman is asking, is it planned to also process preheated manganese ore in the DC furnace, or is the DC furnace only for the Kaimak project? So as the manager of the pyrometallurgy division, I will take some liberties and answer that. So Mintek is known for, we often build a project or a furnace or a piece of equipment for a specific project, but we never use it once. That's the first answer. So we always have long-term research plans. We are currently working on sort of an alternative smelting approach for manganese, if I can call it that, and we are very excited about it, and it will be based on a DC furnace with all, obviously, if you know anything about manganese smelting, there is some interesting things. So we are calling it very ambitiously the improved manganese process, but it will be based on a DC furnace, and clearly that our DC setup will help that. So I would say the answer is a resounding yes, subject to us finding suitable funding and support from industry to test it out. This technology, I think also we should state, is PreMa is not a technology, it's almost more of a concept. Like generally, you have different types of approaches and technologies, but the broader concept is how do we make manganese smelting more efficient? If I'm speaking on behalf of the PreMa team, I apologize. Do you guys want to add anything to that? Thank you. So, is there an option to review the use of hydrogen as a possible reduction in ferromanganese production?
Yes. Again, definitely, it would be. I think that's the way to go. I think hydrogen reduction is definitely in any alloy production.
I agree, because in PreMa we are using, when you're using the off-gas in PreMa, we are using the CO as a reductant because we use the chemical energy as the CO, and we can look into to use. We have in other projects looking into the possibility to use hydrogen as a reductant. It's not as strong at that, but we can have some possibilities. So I think to really look into the possibility to use hydrogen in a pre-treatment with hydrogen, I think that could be very, very, very much valuable. I would really love to have a follow-up of a project on PreMa with hydrogen. That would be, I think that would be very useful.
Yeah.
And linked to the whole using the solar thermal energy to create the hydrogen and so also as part of that work that we discussed last week in terms of it, generating the hydrogen with renewable energy. There's a lot of opportunities there as well. While we were talking, the question was also, is there any consideration to use the CO-rich gas for cogeneration in manganese? I think the answer is yes.
I can also add to that, because in fact most of the energy in the CO gas is the chemical energy, and to reduce the ore more efficient, we will prefer to use it to use the chemical energy and then you will burn it with the oxygen that goes off from the higher manganese oxide. So that is the preferred and the best way. But of course, it's also possible to do a mixture. So we use some of it, you just burn it, and use some of the heat. So you have all of them are looked into.
I think this is more of a comment, but there's a comment that in Tasmania, Temco has a mix of open and closed furnaces, which I'm sure we are aware of. So just
It's similar to Cato Ridge, they also have a mix.
yes.
Metalloys only have closed furnaces, and transalloys only open. But yeah, it does happen.
Yeah. One of the questions here is a practical question. So if you're loading through a preheater, how do you evenly spread your feed into the furnace?
Yeah, happy I understand where you're coming from. Is from transalloys, and they have open furnaces where they use dabblers to spread materials.
Yes.
In the pilot facility, it will be through the basement of the feed port. It's a very, very small furnace. So we will gravity feed the material into the furnace, and then work with the angle of repose to ensure that we get even distribution of the raw materials. But it's an interesting question, and maybe Eli, you can comment on that with the experience with the closed furnaces. How do they ensure this even distribution of the raw materials inside the bigger furnaces? Placement of feeders, I guess.
Yes, I think it's the placement of feeders. So I think this is when it comes to implementation of the technology, this is a very important how we will do this in practice, and we have not looked into that in the project but it's some option to how you can distribute it, or if you're going from it as similar as you do with the charging in the silicon furnaces, or if you can just have several feeders, or it is really something that has to be looked into when you come up to the practical process.
Yeah, so a comment from the gallery is that Autotech has a system for distributing feed from the preheaters via feed chutes out of a shaft preheater. So, I mean, there are a lot of technologies like the Chrome guys who also have to deal with hot feed. So I don't think that this requires a significant development aspect. It's more an integration. Like, you know, I have to get used to feeding hot feed. It's a different way. So to me, always, I mean, one of the reasons if you look at industry, people struggle with hot feed is that it changes the way you have to operate your furnace. So those are the big challenges, and it's one of the reasons we have the TIMAC project. It's not that the DC smelting of titaniferous magnetite has to be proven, nor do we have to prove that you can preheat titaniferous magnetite or pre-produce it, but we have to prove that you can smelt that kind of ore in an open path, in a controlled, sustainable, long-term manner without having to start a preheater as many of the ilmenite guys had to do. So, ladies, we've cleared our deck. I really enjoyed this morning's interaction with you guys, and I think that we should, I look forward to having the school online. I think it would be a wonderful thing. So I'm looking forward to the manganese school, and I hope that before the manganese school we can have another session from you guys giving us insights into the work that you're doing and where we're going. So from my side, thank you very much for your time. The interaction was lovely, and I enjoyed having you both with me today here. And Eli, a special thank you for phoning in all the way from Norway.
Yes.
Thank you very much. Thank you very much, Isabel and Joalet, for allowing me to participate, and thank you all of you for listening.
And lovely for seeing you again, even though it's remotely. It's very nice seeing people's faces here in South Africa, sitting through 35 days of lockdown. Thank you very much.
Thank you.
Enjoy your day. Thank you very much for joining us.
Thank you for the opportunity.
Thank
Bye.
You. Bye.
It's getting serious on this track, fam.